And now there's a question about what other identifications ought to exist. But with the extensional identity type, as we mentioned last time, what we do is we say, well, just to remind you, we say if we have any proof P that A is equal to B, then we just say that A is equal to B in A. So this is the equality elim in the extensional form. Okay, it could be written like that. So we talked about this last time. And it has a number of practical benefits that are important about it, that are very useful, because it says, if you can prove to me the two things are equal, then they're equal in this sense. It prevents us from we can no longer think of the judgmental equality as definitional. It's not a matter of just calculating A and B calculate to the same thing. It's semantic. It has to do with a matter of proof. We have to do this. But we can do this. And then I set you as an exercise that you can use this rule to prove, for example, it follows that, I think I did this, lambda x and x is equal in nat arrow nat to lambda x, 0 plus x. I think I gave an example of something like that. Okay, in fact, it's going to be definitionally equal or judgmentally equal by virtue of the fact that I can show that it is propositionally equal. That's the terminology we'll use. Okay, so it's propositionally equal. So you'll be able to prove that. And that has all sorts of nice and pleasant and useful consequences, because the principles of definitional or judgmental equality say that it's a congruence, so you can replace equals by equals anywhere. And as far as you're concerned, this and that, or you couldn't tell the difference for all the world, and you can replace one by the other anywhere you like, willy-nilly. Okay? It's very pleasant. But it limits the range of applicability of the type theory in a way that is made possible by not taking that as our axiom. So the other one is what is called intentional identity. And this is the one where we're going to get some mileage. So here the idea is that it stresses, you could say the stress is on identity as data. That's the only way I know how to explain to you like the mindset that motivates what I'm going to do next. Okay? So the point of the extensional identity kind of says the identity type should be thought of purely propositionally. We only care about whether it's inhabited. We throw away the inhabitant P below the line, and we just say they're equal. So it's totally stressing the idea that we're going to treat this type, as I say, purely propositionally. It's a firm commitment to the idea that this type is merely a proposition, because the content, the proofs that go into it, get chucked right out. Okay? So a way of saying it is, either things are equal or they're not. Either you have a proof or you don't. Okay? That's a not constructively valid thing, but it's a way of thinking about what's going on. When you do have a proof, then you can say that they're equal. So it's a strong commitment to, this is sort of the stress here is on identity as what we will eventually call a mere proposition. And here as data, so the identity as a full-throated type. I think that's a perfectly reasonable way to describe the mindset that underlies what I'm doing, what I'm going to do now. Okay, so are you with me? Okay, so here's the introduction rule. What I want to do with this introduction rule is I'm going to my mindset, I hope this is helpful to you. My mindset is, this is just a data structure. I don't know, it's some damn type, call it X. Okay, I don't care, right? It's just an abstract type, and there's only one introduction rule, which is reflexivity. So now what I would like to do is to invert this rule. I would like to give an elimination form that expresses the idea that the only thing that's in the identity type is reflexivity. Okay? That's what I want to do. So I don't want to extract from it the idea that since it's reflexivity, well, I better not say that because everything I say has a possibility of me being misinterpreted. Let me leave it like that. Okay, so here's what I want to do. So what is our setup all the way along has been? We say, well, suppose you have a proof that A is equal to B. I'm going to draw a line here. Okay, and this is going to be the equality, oh, I wrote I here. This could, oh, that's the extensional one, yeah. The equality elim, and this will be called int or something, the intentional one. Okay, that's what I'm going to do here. This is a sharp distinction between two forms of type theory. Okay, all right. So the general pattern is of an elim rule, especially when you think, like as I say, think of it as a type that classifies data. If you come along and give me some P, which is a proof of identity, what I want to do is I want to state an induction principle that reasons from, okay, the fact that A is equal to B, as written, you know, that I have a proof that A is equal to B. So I want to reason from A is equal to B. So the way I'm going to do that is, I'm leaving a little bit of space here for those of you taking notes. I'm going to say, well, reasoning from it means, let me call this X and Y. Can you read everything I'm writing? I have a property P, and I'm leaving a little space that I want to prove about Z. Okay? So what's going to happen is, here I'm going to have P of something or other and little p at the end. Okay? So I'm setting it up as an induction principle. You're reasoning from the fact that you've got an element of the equality type. I want to say something about all such element. Whatever that element is, I want to say something such that capital P is true of it. Okay? So what I'm going to do is I'm going to express an induction principle that is based on the reflexivity axiom that says, well, it's enough to consider, break it down by cases. Look at all the intro forms. So with mathematical induction, we had two premises here, one for zero and one for successor in terms of the predecessor. Here I don't have any predecessor within the identity type. There's no idea of a predecessor. So it's a case analysis. And not only is it a case analysis, but it's a one-way case analysis. Okay, there's only one case to consider. Right? This is an inductive type, you can think of it as, that has only one case to consider. There's a major league subtlety coming up, but we'll get there. Okay, back to this as a technical point. What I want this P to be is I want this P to hold, it's a predicate about any identity type in A. So it's written P, X, Y, Z. Because, you know, otherwise the X and the Y would be dangling. If I just said P is a predicate on proofs of equality, okay, then what would the X and Y be, okay? So just as, the only way I know how to draw the analogy is, just as when you're doing a principle of mathematical induction, the inductive hypothesis considers an arbitrary natural number such that the IH holds, and then deduces that it holds for the successor, right? So you have a parameter there, X, which is an arbitrary natural number, and you go from X to X plus 1. So here I have a parameter, it's X and Y, and this is a proof, a parameter, that X and Y are equal. And then I'm going to prove a property that has three positions in it, X, Y, and Z. Okay? So I'm going to derive a ternary, the most general cases, I derive a ternary relation, okay, out of the, I'm going to drive, and so what will go here will be A, B, and P. So if I have a particular equality, if you give me one of these, I want to show that it holds for A, B, and P, for that particular scenario. That's what I want to do. So now comes the important question. What goes here and what goes above the line? And this is going to take some getting used to, I think, for most of you, because my experience has been, it's confusing. And in fact, I'm writing my notes yesterday and I got confused. So I know that it'll be confusing. Okay, so the idea is this. It's enough to consider reflexivity. just like in mathematical induction, when you want to prove something about an arbitrary natural number, it's enough to show that it holds for every numeral. And the concise way to say that is you show outright that it holds for 0 and show that it's preserved under successor. And that way you know if you give me any numeral s of 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 0, that the property will hold for that. In effect, you're saying you're doing an infinitary case analysis, one for each numeral. That's what mathematical induction is doing. So here I'm doing a unary case analysis, one for each introductory form. There's only one, REFL. So what I do is I say it's enough to show for any x in A, you have a proof, I don't know, I'll call it Q, of what? Of P, x, x, and REFL of x. And if I can do that, then what I have is a proof term here, which is traditionally written J. And J takes an argument. It's parameterized by, a lot of times I'll miss it out, but right now let me just write it down. So here's the family. You have to remember what family are you eliming toward. So that's some kind of an argument, okay? And then you are using x.q as your proof, so to say, your inductive step, for lack of a better terminology, okay? And you are using p as the argument to it. So that is the, so this could be thought of, this could also be written as, and it sometimes is in a more systematic account, this is the recursor for the identity, in the same way that what I called rec last time is the recursor for the natural numbers. All right? Yes?
Can you explain the notation in the square brackets?
Oh, it's just my personal notation. There are various people. Sometimes people will write J sub X, Y, Z, P. It's somehow getting across the idea that it's a bit ancillary. I'm just like, to be careful and thorough, I really need to inform J what family it's working toward. And then it takes as somehow the meat is the proof of the, well, I don't know what to call it, the induction step. I guess that's what you should call it. And then the path or the proof that you're working on. There's different notations. And in fact, in practice, we'll often leave those out. But as I'm going to show you in a minute, the first few times around, you definitely want to write this down so that you don't get lost. And you watch, I'm going to screw a proof up. I've written it out several times, and I know I'm going to screw it up because I always do. So I'll try not to screw it up. But you'll see that this is the way to keep your bearings. And now there's an important thing. There's a definitional equality. Yes?
So just a notation question. This J is a term constructor, and the J you had the first lecture?
What's that again, sir?
The J you had the first lecture was a meta variable, right? This J is different than the first J you saw.
This J is different than what?
You use this J as a kind of notational trick, which is a different J, so you can sort of collapse the judgments.
I don't know what you mean by that. I'm not sure I'm getting at that. What? I don't think I had a J on the table before.
I'm mistaken.
Okay. Oh, an arbitrary judgment. Oh, okay, yeah, sorry. That was a script J, whether I wrote it that way or not. The only way it's just that this is the tradition. Martin Luther called it J, so there's no, like, obviously good reason to call it J, except that it comes after I or something. I don't know. But the thing is, the recursor for the identity. It's a particular term-forming constant. It's the, okay, and this principle, by the way, for reasons which I'm going to explain now in a minute, is called path induction. Oh, okay, so there was a question then. There probably are many. Okay.
Can you explain the upper right premise that involves x, y, and z as assumptions? Yeah. What is it for? What is that doing?
What are the?
I don't understand why we need that premise.
Well, because remember, the general pattern of an induction principle is you're reasoning from a type of interest toward something. So the thing I'm reasoning toward is this P. And P has three arguments: the left and the right endpoint, and the proof that they're equal. This is just like saying, you know, if you have a predicate that you want to prove about x, y, and z for any x and y which are equal, and any proof z of that fact, it's enough to show that you can prove P given that x and y are identical, and that the proof in question really is reflexivity. That's what this is saying.
So I'm just setting up the fact that we have a P.
Yeah, you have a P. Yeah, that's all. That's like just the data. Did I? Okay, Todd, yeah.
You probably want to colon U there after the P.
Oh, yeah, sorry. Oh, maybe that's what's confusing people. Yeah, so that's a type, and this is colon U. Yeah, yep, thank you. Yeah, that's exactly what I messed up. Yeah, sorry. Yeah. Yeah, sorry about that. Yeah. Okay, yeah.
So what's that x dot d and that d inside the braces?
Why what?
Yeah.
Why did I put it in braces?
No. What is that x dot d? Q. Yeah, Q. Is that the Q or the?
That's a Q. And P is the starting point, which is the proof that A is equal to B.
But what are those parameters to the identity recursion?
P is here, and Q is here. Q has the variable x in it, and P is just an outright proof of equality.
So J is like some constructor taking those two guys.
That what, sorry?
J is a constructor taking those two guys.
Yes, exactly, yeah. Yeah, well, it's a destructor, actually, in the terminology, but yes, it's an elim form, yes. Go ahead.
How do you read the J term again?
How do I what?
How do you read the J term again? How do you read it?
How do you read it?
Yes.
Well, maybe what I'm about to say is going to help you. So what I'm about to say is, what is the principle of definitional equality that applies to this? What is the computation rule? Maybe that's what you're getting at. How do you compute with it? Okay? So let's write it. Let me just miss out the subscripts. That's what people typically do. Okay, you've got a proof that holds for any x and REFL, and if you actually give me REFL, then that should be the same as plug in A for x and q. And if you look, that means that this is of type P of A. Look in the second line there of the rule, P of A, and REFL. A of A, which is this guy. So if this is my P, then this is my P here, okay? And P is between A and A. That's the notion of definitional, that's the definitional equality that governs the J. Okay? So that they are, yeah, that's the definitional equality. So it's a recursor. It doesn't have any real proper inductive structure, so it's really a case analysis. And it only has one case. So there's only one case it could be. So if you look at the recursor for plus, for sum that I gave last time or whatever, it had a case analysis. It had two cases because that was how you think about the sum. It has two things. We gave abort, which was a case analysis based on 0 cases, okay? Because there's nothing in the empty type. Here we're doing a case analysis based on one case. This is a subtle business, so right now I'm approaching it purely formally. That is, I'm just saying, if that's the intro rule and you think of it as a data structure, pretty much you've got to give this as your elim rule. That's like pretty well forced on you just by using the patterns of reasoning that I've developed so far. Okay, got me? All right, now we're going to really get ourselves into a lot of trouble. Okay, yes?
What do you mean by x dot q? Does it only...
X is bound within Q.
Okay, so
Yeah.
q is a formula with x free in it. X is
Yeah,
free in q.
well, it's not free, it's bound right here by this binder, okay? So,
Comment about that. So essentially, if you like imagine that there's a lambda term before x, y, z.
Yeah.
So like he's omitted it because there isn't actually a lambda. But if you like stick it in there, they're binders. So the x's in the brackets and the x's are not.
or to put it another way, lambda is just an instance of the general scenario. If you have lambda, it takes one argument, x dot, A. You have other things like case, which take several arguments which bind different positions, y dot b, and then it also has a c, etc. Okay? So that's the theory. So what I'm doing is using ideas from logical frameworks, and this is like the idea of a second order abstract syntax. So you can, I hope, like I said, there are certain things I'm glossing over because it's unavoidable, okay? I absolutely, positively would put you all to sleep if I went through all the details of everything I'm doing. So, okay. Okay, so that's the J. So now comes the very interesting thing to do. Okay? So that's the elim form for the identity type. So I've been calling this thing the identity type. Okay? And I've been stressing that it expresses equality. So surely it had better be an equivalence relation. Okay? So that's the important thing. So I would like to say, the first thing I want to say is, fact, this is kind of surprising. See, if you look in any axiomatic account, like in first order logic, of any kind of thing, like an algebraic theory, or practically anything in sight, somewhere they will say, oh yes, there's this relation called equality, and the axioms tell you it's reflexive and symmetric and transitive, amongst other things. But anyway, that's what they'll tell you. Okay? There's no axiom for symmetry or transitivity in this formulation, because it's a theorem. And that should surprise you, because it's not obvious. Okay? So I'll show you how it works. It works by path induction. So the way you would say it is, I'm going to write it in 3 different ways to emphasize what's going on here. I could just say loosely, equality at A is symmetric. Or a little bit more precisely, I could say, well, for every x and y in A, if x is equal to y, then y is equal to x. Or I could write that in English. The thing that you're going to have to get used to that is beautiful in my mind, okay, like something I love, okay, is the idea that the math statements you make are types. And the proofs you write are programs of that type. So I need to write a program of that type. If you wanted, you could say, for all x and y in A, if you want, that's fine. If x equals y, then y equals x. That's what I'm expressing here. Okay? That's what I'm doing. And what I really mean is, when I write that out like that, I really mean there exists an element here. It has an element. There's some kind of element of that type. That's what it means to say that this is true, is transcribed into here via propsis types into a type. And when I say that this is true, so let me just write it as blah, 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 true. I won't do that very often, but I'll do that. Because, you see, what happens is, in the conventional math, when you write theorem A, you say some big proposition here, that's just the conventional notation for the judgment A true. Okay? And when you write after that proof little a, that's just the conventional notation for A as in A. Okay? So we're going to do that a lot. Okay? So a lot of things will be written. But then it opens up, as soon as you start to realize that, it opens up lots of possibilities that we're not completely used to. So what I'm going to do is, here is a way to say this is, what I'm going to say is there's a function like this, but another way to write the same thing is to say, if I have x in A, and I have y in A, and I have a proof that x is equal to y, then I have a proof, which I will fill in here, that y is equal to x. This is clearly sufficient for that, because if you look at the rules, this is exactly what you need to prove in order to prove that. Okay? And I need a name. I'm going to give a name for here for this thing. And we could call it sim, the symmetrization of Z. But very shortly, for reasons that will become apparent, we'll also sometimes write this as Z inverse. Okay? So this is what, this is the idea, so this is the idea of symmetrization. So this is the one I'm going to be interested in. So what I'm really saying is, there exists a term like that where And here's what I need to know, or such that. Let me write such that. This will be very important. I'll write it over here. So there exists such a term, such that if I symmetrize reflexivity, I get back definitionally reflexivity. Which is a way of saying, if you think of reflexivity as, this particular notation is used a lot, but it's a little misleading, is I'll write ID inverse is equal to ID. Because if we think, and if you want to write sub A, that's okay. The problem with this notation is it confuses it with the identity function. So this is really just a notation for REFL. And really, a lot of times people will write ID, but it's confusing because they'll also write ID for the identity function. Okay, and that's, I'm sorry. So I'll try to write REFL here and not write ID very often, but you might as well get used to the fact that one of the notational abuses that comes up is writing ID for REFL. Okay, so this is the interesting part of the theorem. This is like a progressive refinement of expressing as precisely as I know how the information content of the symmetry of equality. It means there's a mapping. So here's what I'm heading toward, okay? Here's why I care so much about this. And I need to leave that picture there. So let's go over here for your reference. Okay. Okay, so the picture that we're going to have is this. We have this notion of a space A, and we're going to consider in general the notion of identifications between two elements, let's call them A1 and A2, which I'll write as a line, and sometimes label it P, which is a proof that A1 and A2 are the same. Or if you like, that looks a little cluttered, I can write it as a line. It won't look too good on the board, but in the book we write it as a double line, okay, to sort of say it equates A1 and A2. Another times, depending on your particular mood and scenario, people will write like a squiggly line, okay? And the idea is that this thing will be thought of, identifications are to be thought of as paths in the space. And I'm going to tell you why path. Why is it a path? Well, I'm going to think of it as a way of, you might say, walking from A1 to A2. That's one way to say it. Another way to say it, and we'll see, because that idea I presaged there about vibrations will exploit all of this, but I'm going to do some iterative deepening. That's what I'm doing here. So you can think of it as walking from here to here. You can also think that the space is deformable in such a way that by moving A1 along that line, I can move it all the way over to A2 all the way over to A1, or conversely, A1 over to A2, okay, to turn that path into a loop. So I can deform this so that this path becomes a loop here, or it becomes a loop here. Because the identification is a pathway by which I can deform the space to make the endpoints be identical. Okay, that's going to be the idea. And why do I call this paths, and why am I doing this? So if you look at this self-loop, so then now there is a notational problem. There's a notational problem, which is how to notate. Let me make this smaller. Well, okay, let's say we'll leave that alone. That's like I was thinking of that as the deformation. But associated with each point is, well, a little loop. I'm sorry, there's no other way to draw it. There's a little loop, which is the one that doesn't go anywhere. So the problem is, I can't draw that. The one that doesn't go anywhere, as soon as I draw something, I've gone somewhere. So you have to understand when I write it as little one, okay, that what I mean is it's the one that doesn't go anywhere. I don't know any other way to notate the damn thing. So one notion of a path is you don't even take one step. You do nothing whatsoever, and now you've gone from where you are to where you are. Okay? So that's the reflexivity, yes?
The path of length 0.
What's that again?
The path of length 0.
You could say it's a path of length 0, yes, exactly, yes. It's just that there's no notion of length in homotopy theory. So the idea about, this idea, I should mention this as well because it's germane. You have to understand that we're abstracting away from any kind of geometric considerations. There's no notion of length and there's no notion of angle, okay? Everything can be deformed and twisted and squished and stretched at will and never without changing a thing. Because we abstract away from any concept of how long something is or what an angle might be, which is another kind of measure of things. All the geometric considerations are eliminated. So we're only concerned with the possibility. But we'll often use notations and diagrams that look a little, geometric in a way. And I'll give a specific example of that shortly. So here's the thing. There's always the path that doesn't go anywhere. You could say it's of length 0. That's fine. Okay, as long as we understand that length has no meaning geometrically. It's just convention. So the path that doesn't go anywhere is reflexivity. If I have a path from A1 to A2, I can reverse it. That's what symmetry is saying. And really, what I'm saying is, if you can go from A1 to A2, then there's a path that goes backward, okay, that follows that path backward. I'll give it a direction in this way. And then the third thing is, if I have another point, A3, then if there's a path from A1 to A2 and a path from A2 to A3, then there's a path, namely the composition of these two, which goes over to here and goes over to here, which represents that path. Okay? I can write it like that. And now, the interesting thing is that the reflexivity of the possibility of the null path, let's call it, means that equality, if we think of these identifications as equalities, means that equality is reflexive. The possibility of the symmetry of equality expresses the fact that if you can walk over to here, you can always walk backward. Okay? You lay your breadcrumbs and you follow them back. Okay? The transitivity, which I'm going to explain in a minute, the transitivity of equality says that you can compose paths. The reason, if A1 is equal to A2 because there's a path, and A2 is equal to A3 because there's a path, then A1 is equal to A3 because there's a path. But I don't merely say, if there exists, then there exists. I say, if you give me the path P, and you give me the path Q, then the path that's here is called P dot Q. P followed by Q. And this is the path P inverse, which is walk P backward. Okay, so this is our first idea. We're going to deepen this momentarily. Okay, it's not even. I still haven't said enough. There's even more to say. Okay, about this, but it's the beauty of proof-relevant math. Okay, so we're going to say there is a way which has this property, and that's the interesting thing. If you take the null path, given my problems with drawing the null path, if that's the null path, and if I run it backward, I can reverse that, which means I can go from here to here. It's still the null path. That's what this is saying, okay? Because I never went anywhere, so doing it backward is still not going anywhere, okay? So that's the idea. Okay, yes?
Is that supposed to be a triple equals on the ID -1 equals ID?
Right here is, yeah, so this is that, a triple equals, yeah. Is that what you meant?
Yeah.
Whoever's saying that, I don't know, yeah. So yes. So how do we prove this, okay? So what we do is we prove it by path induction. So what does path induction tell us? Path induction tells us if you want to show something about an arbitrary path between these endpoints, it's enough to show it for reflexivity. So informally, it suffices to assume that Z is reflexivity at A, where A is equal to B. They're the same. Well, now I have a problem. Okay, reflexivity at X. let's call it reflexivity at x, okay, which is what is going on. That's the idea of path induction, okay? Because if I want to show some property holds for an arbitrary, so my property here, right, the property here is this guy, okay? So I have an assumption, okay, that x, so in other words, this is going to turn out to be a j term. This is going to be some j that I'm going to derive. That's what's going to happen, okay? So what I'm going to do is I'm going to prove that my p, this is going to play the role of p here, and we'll see exactly what p is here in the moment. The p doesn't actually depend on z at all. It depends only on x and y. So this will be my pxy. It's a binary. It's a degenerate dependency. In general, the property gets to say something about z, but I don't need to. The property in question, that it is a proof of y equals x, doesn't mention z. So I'll drop that out. So that'll be my pxy, okay? So the idea is it's enough to show that given x in A, I need to show that there's a proof that p holds, this property pxy holds for x and x. That's right here. Since the z is not playing a role, it's enough to show p holds for x and x. So I need to show that there is an element of the type x equals x. And of course there is. It's reflexivity. Okay, so I have that. So therefore I can define symmetrization of z, as it's written here, can be defined as you're doing a j. Oh, by the way, this thing is called the motive for the induction.